again, just as yesterday, we've got 2 hours this afternoon, now from 2 to 3, then a half-hour break, and then from 3:30 to 4:30. Dan, back to you. Thanks.
Welcome back. Thank you, Frederick. So the second part of today's tutorial or introduction is going to focus on unmeasured confounding, so settings where you haven't measured all the relevant variables, and sort of both kind of from extending what we've talked about already a little bit, like the constraint-based search, to a setting where you haven't measured all the relevant variables. And then the sort of second half of the second half, I'll talk about some more recent alternative approaches to causal discovery that aren't necessarily neatly in the constraint-based or the score-based paradigm. So far, what we've talked about today in the phrasing the problem as learning a DAG or an equivalence class of DAGs has kind of taken on this fantasy of having observed all the relevant variables in the problem that we're studying. But of course, in reality, in almost any application you can think of, perhaps there are some exceptions, but applications in genetics and in neuroscience and in the social sciences, there are the real causal processes probably include a bunch of variables that are not represented in our data. Unmeasured variables, I'll call them latent or hidden variables, and I'm just using these as synonyms, pose a real problem for reliable causal inference, drawing reliable causal conclusions in a lot of domains. So the one way of thinking about this is to broaden the starting point to assume that, rather than assume that there's some true causal DAG over the x's, that rather there's some larger DAG over a larger variable set, which I'll just call X union L. So X will be the observed stuff, and L stands for latent. And so this can be a vector of any size you can think of, that they're not restricting the cardinality of the latent variables in any way, but we only observe X. So we observe some, reduction or marginalization of this larger causal process. And thinking about this kind of to try and introduce some intuition, just thinking about 2 variables at a time, say you have X and Y, and you know that they're associated, known to be dependent. So what are the possible causal processes that can explain this dependence or give rise to this dependence? Well, obviously, it might be that there's a direct causal relation between the 2 of them, which goes in one of 2 directions, from Y to X or X to Y. It might be that neither causes the other, but rather there is some unmeasured common cause of them both, L, a latent factor. It might be that common cause coexists with a direct causal relationship, so they might exist together. There might be some sort of feedback relationship if you think of X and Y as maybe measurements of some equilibrium process. So interventions on X will change the distribution of Y, and interventions on Y will change the distribution of X. Or there might be selection bias. So it might be that they only appear associated because X and Y both influence the process by which the sample was taken. So if you think about selectively sampling from some population of interest, if you selectively sample on the basis of X and Y, in the conditional distribution, X and Y will look associated, even if they're not causally related to each other. You can actually see this based on stuff that we learned previously. This is a kind of collider, right? So conditional on being S equals 1. So say S equals 1 means you're in the sample, 0 means you're not in the sample, X and Y will look associated. And combinations of the last 2 can coexist with all these other possibilities. I'm going to ignore the last 2 possibilities for the purposes of this talk. So I'm going to assume no selection bias and no feedback, no cycles, and just say that there's this finite set of possibilities that can give rise to any observed association, either a direct causal relationship in one of 2 directions, a common cause, or a combination of those. So how could we, so if those are, that's kind of nice because it's just a finite number of options really, right? There's only 5 structures up here, and you might want to distinguish between them or among them. How could you possibly distinguish between these possibilities from observed conditional dependence facts? Well, in general, with just those two variables, you can't, at least not without making additional, stronger assumptions. So we can distinguish between those different possibilities with just x and y, because they all apply the same restriction on the observable distribution, P of x and y. That's the thing that we have available to us to make inferences from. In particular, no restrictions at all. They just all imply that there's some association between x and y, so it doesn't factor x. However, with more than two variables, patterns of independence may emerge, which can narrow down the structure, at least when you make additional assumptions like faithfulness. For example, so say now I have three measured variables and one unmeasured latent. So if this was the true structure that generated my data over these three variables, we can see from d-separation that y and z are not independent given x, or at least they're not d-separated given x, so given faithfulness, they're also not independent given x. Why is that? Because there's a deconnecting path that goes through L, right? So z to x to L to y is a deconnecting path, and so they'll be conditionally dependent. Whereas if there wasn't such an L, if there was no L that was a common cause of x and y, now d-separation tells us that actually z and y are independent given x because they're d-separated. So that means that there's a difference in the implied conditional independence constraints between these two models over just the observables. So z, x, and y are observables, L is not. And there's a difference between what these two models, if these were the only two models we were going to consider, we can test this conditional independence and decide between the two models. To make things a little more complicated, you can imagine larger patterns that emerge with more than just a few variables. So this particular graph, I should say this graph and the previous one might look kind of familiar to you from a kind of instrumental variables perspective. And the kind of interesting thing about this structure is that here's an example where it sort of seems like I have two things that act as instrumental variables, if you're familiar with that, in the sense that there's no effect of the z's on the outcome except through the exposure or treatment x. And this particular DAG implies over the set of observables this list of conditional independence constraints, right? Assuming this following from d-separation and faithfulness assumption. Whereas this structure in which there is no such L implies a different set of conditional independence constraints. So we can just flip, for example, if you look at the bottom two, it's about whether y and z's are independent given x's. Yes.
The previous graph is if you condition on x, shouldn't z and z still be different?
If you condition on,
never mind. Sorry.
So it's a collider, so they're going to be.
Yeah, I was looking at the long path. Anyways, yeah.
Yeah, no worries. So the reason I like to put this example up is because in the kind of algorithms that I'll talk about in a second, like the FCI algorithm, these kind of like Y-shaped structures where you have sort of independent sources of variation can be very informative about the presence or absence of unmeasured confounding between something you care about like X and Y. And we'll see that in the algorithm I present that like the arrows in which it's identified whether that arrow hides an unmeasured confounder or not are exactly ones of this kind of form. They're ones that in which the covariates give you a set of conditional independence constraints that distinguishes the latent model from the not latent model. Here's another example. In some cases, a pattern of conditional independence may suggest to you unmeasured confounding because there's no non-confounded model, no DAG model over those variables that satisfies the observed set of conditional independence constraints. In particular, if this were the structure, if I had an unmeasured variable here, L, then again, just using d-separation and faithfulness, you get a set of conditional independence constraints. And you should be able to see that there's no DAG that will satisfy exactly these independence constraints over these 4 variables. Why is that? So if I imagine a DAG over these 4 variables, in order to satisfy these dependencies, it has to be there has to be some edge between x2 and x3, right? Because they're dependent. And I have to orient it in one direction or the other. But if I orient that edge from, say, x2 to x3, then that should imply that x2 and x4 are marginally independent but dependent when I condition on x3, right? Because it'll be a collider. But x1 to x2 to x3, in that case, would be 1 and 3 would be independent given x2. Maybe it helps to draw this. So I can imagine so if this were the DAG, then I would have x1 independent of x3 given x2. But that violates this constraint that is implied by the model. Or if I oriented the edge in the opposite direction, then x2 should be independent of x4 given x3, but that violates this constraint in the model, right? So it's a kind of quick proof that there's no DAG model that represents exactly this set of conditional independence constraints. So you have to sort of posit something else, like an unmeasured confounder, to explain this pattern of conditional independence constraints. So the way that we do this is by leaving behind the class of DAGs and CP DAGs and start thinking about a broader class of graphical models, mixed graphs. So mixed, just generically referring to having multiple kinds of edges. And in particular, mixed graphs here will refer to graphs that have both directed and these bidirected edges, where the bidirected edges, similar to what you saw in the presentation yesterday, represent unmeasured confounding. So this model is represented by this graph, and that captures just the conditional independence relations on this list. So the nice thing, so fortunately, there exist procedures that allow for arbitrary latent variables, arbitrary in the sense that we're not making any assumptions about how many there are or which other variables they might affect, or distributional assumptions about them, really. And they search in this kind of larger space of mixed graphs. Specifically, I'll spend a lot of time over the next hour talking about a constraint-based procedure, which follows a very similar logic to the PC algorithm called FCI, which stands for fast causal inference. So we're going to sort of abandon the hope of finding a DAG or a CP DAG representation and search over this larger space of graphs. So there are these mixed graphs. This example I have over here is specifically an acyclic directed mixed graph, which is often abbreviated ADMG. And there's a procedure for taking a latent variable DAG and constructing the implied ADMG graph, which is a unique construction from latent variable DAG to this mixed graph in a way that preserves all the conditional independence information among the observed variables. And that procedure is called this latent projection. So if I begin with a DAG G and think about the induced dependence structure when some variables have been marginalized out, which is kind of the mathematical operationalization of having not observed the variable. I want to preserve the conditional independence relations in the marginal distribution, meaning over the x's, and represent those with an ADMG. So this latent projection operation starts with a DAG over vertices x and L, and spits out a new graph with vertices v prime and e prime in the following way. So the vertices v prime are just going to be over x. And there's going to be an edge between any two x's if there exists a directed path from xi to xj in the original DAG, with all intermediate nodes on the path belonging to L. And the sort of special, a directed path that doesn't go through any L is a special case of this because there are no nodes on the path, right? So if I have a directed edge between xi and xj, then all nodes on the path go through L vacuously. There are no nodes on the path. And so I'll always put a directed edge in the latent projection. And then there'll be a bidirected edge, this double-headed arrow, if there exists a path from xi to xj of the form, with an arrow-headed xi and an arrow-headed xj, where every intermediate node on the path is in L, and no consecutive edges on the path are of the form of colliders in L. So I'm sort of excluding the possibility that there are these colliders on the pathway between xi and xj. So this is a sort of way of saying that there is a deconnecting path between xi and xj through stuff in L. And that induces a dependence between xi and xj in the marginal. And the nice thing, although it may not be the most, well, let me just go through a couple of examples. This first one we saw up here, the latent projection of this is the graph that we had seen 2 slides ago, right? It has a bidirected edge between x2 and x3. Why is that? Well, all these directed edges get carried over automatically because they satisfy that first condition that, that there's an edge between them, a directed path between them with all intermediate nodes on the path. And there's a bidirected edge between them because they satisfy the second condition, namely that there's a path from where L is this variable in the middle that goes to xi and goes to xj. So that sends us from this latent variable DAG to the ADMG latent projection. And importantly, this other graph, which is a different DAG over a different set of variables, implies the same latent projection, right? If I follow the logic, I'll still just get an edge from x1 to x2, from x4 to x3, and a bidirected edge between x2 and x3. So really, an infinite number of possible latent variable DAGs can get projected down to the same ADMG as long as they represent the same d-separation relationships between the x's. Okay? And the kind of nice thing about this construction is that ADMGs preserve conditional independence relationships among the observed variables using a criterion that's basically just d-separation, but for mixed graphs. So d-separation is, the d stands for directed. When you talk about mixed graphs, you talk about m-separation for mixed. And I won't formally define it here, but it's literally just the same definition of d-separation you saw yesterday, but just allow for the fact that arrows have 2 possible endpoints. They could be bidirected or directed, and you get m-separation. And the result is that for any set of any 3 sets of variables, they're d-separated in the DAG if and only if they're m-separated in the ADMG that's created by latent projection. So it's kind of like latent projection is created to preserve this kind of conditional independence relationship. Any questions on this before we go on? Yeah.
So why is the case that, so we're allowing, I think, in the definition for a variable L to affect many observed variables, like it could affect 3.
Yeah.
And so why is it like not useful? I asked kind of this yesterday, but why is it not so useful to consider hyperedges to describe when L, I mean, it blows things up combinatorially, but why can we really throw away that and just think pairwise? What's the probability intuitions behind that?
Yeah, that's a good question. So you might, so sort of to summarize, the idea is that you might think that you can distinguish in your latent projection between latent variables that are causes of just 2 observed variables versus 3 or more observed variables. And you could come up with a representation like that. I think the point is that here they're not needed because d-separation only really cares about the endpoints of pathways. right? So like the point is that it's all constructed to make this true. So deseparation between sets is like just deseparation between all the elements of each set on either side. And so the criterion for deseparation is like, is there a path from x1 to xj that satisfies some properties, right? So if all you care about is preserving deseparation relationships, you just need to know, is there a path that goes through L's in the right way or not? And so I would agree that you could do this construction that's sort of more informative in a sense, but it's not going to be more informative about deseparation.
If I could just say something about that. So just, okay. These properties of deseparation or deconductivity, in other words, whether what's faithful or not, sort of it's the same. But it's not true that the set of probability distributions supported that are consistent with the graph are the same. So if I have a chain and I have a single hidden variable that kind of can talk to all the visible variables, that's not the same thing as having many hidden variables that each speak to just two at a time. The class of probability distributions supported are not the same, but the deseparations are the same.
Yeah, they're the same independence model, but I think the illusion is that there's other potential implications of a latent variable model that affects a bunch of things at the same time. For example, in a later workshop, you might talk about like inequality constraints between the measured variables. And those are all just sort of ignored by this criterion for now. So it's the same independence model among the marginal is the kind of way that I would put it. Okay, so ADMGs are cool. They have this property, which is nice. So they also have a relatively clear causal interpretation because you can easily think about the causal DAG that generated them, right? Like you can see that if I give you an ADMG, that directed edges represent that there's a causal pathway from one of the variables to the other, and bidirected edges represent that there's some unmeasured common cause of them both. So that's nice. And there's a lot of associated theory for ADMGs. So yesterday you learned about the ID algorithm, and there's sort of general identification results for if I give you an ADMG, how to calculate post-interventional distributions of various sorts, or even more complicated kinds of interventions, soft interventions, stochastic interventions, whatever. There's a lot of theory for identification of causal quantities given an ADMG. But they're not ideal targets for structural learning or causal discovery, at least not yet. And the reason is that so there's a few reasons. The first one is that Markov equivalence for ADMGs is complicated. So with DAGs, there was a really simple characterization of Markov equivalent DAGs, right? Same adjacencies and same unshielded colliders or immoralities. So that's how you can check whether two DAGs are Markov equivalent. And then there was a representation, a graphical representation of the entire equivalence class, which is also quite neat. It was just like a graph with directed edges and undirected edges, and we could characterize the properties of that representation. For ADMGs, there is no such nice thing. So Markov equivalent graphs might even have a different number of adjacencies than each other. And so there's not going to be one convenient graphical representation that you can use to summarize the Markov equivalence class, which means you can't search for the Markov equivalence class in a straightforward way. Secondly, and this is maybe not so important for present purposes, but parameterization of ADMGs is kind of complicated. So if I give you an ADMG and I say, I want to associate with this like a linear structural equation model, it's not as simple as in the case of a DAG to say that the linear structural equation model has parameters theta 1, theta 2, whatever, and that implies all the same distributional properties that the ADMG represents. It's simple in some cases, but complicated in others. And then perhaps most importantly, for the purposes of what I'm talking about here, which is a kind of constraint-based search procedure, is that ADMGs are not maximal. The maximality is this property of a graph that a graph may or may not exhibit, which says that for every pair of vertices, a non-adjacency implies that there's some separating set, meaning there's some set that makes them conditionally independent in the associated model. So this was true for all DAGs, because deseparation just gives you this. So if they're not adjacent, that means they're deseparated given some set, and that means they're conditionally independent given that set. But ADMGs don't have this property automatically. So there may be missing edges that don't correspond to any particular conditional independence or separation of this sort. So as a kind of classic example, here's an ADMG on 4 variables, which represents this kind of latent variable model between x2 and x4. That's not maximal. Can anybody identify why?
Can you go back to the definition
Yeah,
of
yeah.
maximality again?
So it's not maximal if there's a non-adjacency that doesn't have a corresponding conditional independence over the x's. So there's only one, as a hint, there's one non-adjacency in this graph between x1 and x4. Otherwise, everything else is adjacent. I think that's all I have in there. Yeah.
Yeah, so if you condition on x2, there's a path from x1 to x2 to x4. And if you condition on x3, there's a path from x1 to x3 to x4. So
Right. So conditioning. So you have to think about what are the possible deseparating sets in this graph between x1 and x4. There's the empty set. There's x2, x3, and x2 and x3 together. And the question is are the paths between them deconnecting or not, given those conditioning sets? So as the simplest one, x1 and x4 are they deconnected given the empty set? Yes, there's just like this direct and deconnecting path between them. So they're not deseparated given the empty set. And then you ask, are they deseparated given x2? And no, there's a deconnecting path even when I condition on x2, because x2 is going to be a collider. So I will go this path, for example, and I'll make them deconnected. X3, similarly, if I condition on x3, are they deseparated given x3? No, there's a deconnecting path such that all colliders on that path, I forget which definition you guys learned yesterday, I think in terms of deconnection. So here's a deconnecting path this way, and I condition them both, and it's the same thing again. So no matter what I condition on, there's a deconnecting path between x1 and x4. So it means there's no deseparation between them given any subset of the variables. And so that missing edge does not correspond to any deseparation. So that's inconvenient from the perspective of causal discovery or structure learning, because when we talked about the PC algorithm, sort of a key step was that whenever we observed a conditional independence, we could remove the edge, knowing that there was some sort of deseparation between them. But you can't do that with general ADMGs. So this is what motivated thinking about a kind of specific subclass of ADMGs called maximal ancestral graphs. So in order to make a kind of PC style search possible, where I can test conditional independence constraints and remove edges from some sort of supergraph, we'll focus on this class of MAGs. And for the purposes of our present discussion, think about MAGs as just a special case of ADMGs in general. There's a footnote here which says that actually the sort of full definition of MAGs is a bit more complicated and allows for directed, bidirected, and undirected edges to coexist. And that's because MAGs were sort of in part invented not only to deal with systems with unmeasured confounding, but also with that selection bias problem that I alluded to earlier. But I'm going to just ignore that for the purposes of this talk. It just makes things more difficult to write down. But if you go back to like the original MAGs paper, you'll see all the theory proved with directed, bidirected, and undirected edges. So for our purposes, we'll define a MAG as follows. Firstly, we need a kind of name for variables that are connected by a bidirected edge. So we have parents, children, ancestors, all these things. So we're going to call edges connected by a bidirected one spouses, SP. Don't blame me for this. I did not come up with it. We're going to define an ancestral graph to be one in which no variable is an ancestor of either its parents or its spouses. So the first part of that, if you ignore the spouses bit, it says that no variable is an ancestor of its parents. That just means no cycles, right? So that's true of DAGs as well. If you were an ancestor of your parents, there'd be a cycle from you to you. But sort of the additional bit here is that there also can't be a path from a variable to any of its spouses. So those are paths that kind of look like this. Like you can't have a path that leads you to be an ancestor of any of your spouses. So that's called the ancestrality property of a graph. An ancestral graph is one that satisfies this property. So it does not contain any directed or sort of almost directed cycles. Okay. So that's a subclass of ADMGs. And then a second step is that we're also going to restrict to ancestral graphs that are maximal. So ancestral graphs that satisfy this maximality property we discussed a few minutes ago, that any missing edge corresponds to a conditional independence. And there's a construction for how you go from a latent variable DAG to a MAG that we'll get to in just a second. But before that, let me say that MAGs have pros and cons as a kind of object of inference. The major pro is that they're maximal by construction. So if we ever find a conditional independence, we know that that corresponds to some sort of missing edge, and we could do a kind of PC style search. The second benefit is that you can characterize Markov equivalent MAGs, maximal ancestral graphs. There's a few papers that have gone through the hard work of defining both how to check if two MAGs are Markov equivalent and represent the entire equivalence class of MAGs for a specific graph with a single graphical object, which we'll get to in a second. It's called a PAG, a partial ancestral graph. And then on top of that, they inherit other nice properties of ADMGs, namely that M separation works out in all the same way. So if two variables are M separated, given a third in the MAG, then they're D separated given that variable in the underlying DAG that was used to construct the MAG. So those are all nice properties that MAGs have. The cons, however, is that they're going to have a much more confusing interpretation or indirect interpretation, causally speaking, as compared to ADMGs. Not that you can't, like, if you spend time with MAGs, the interpretation of them becomes, I think, somewhat intuitive eventually, but it's like not easy to just read it off in the same way that it's easy with DAGs and ADMGs. And I'll get to what I mean by that in a second. And also that they're less informative than ADMGs in a sense that MAGs will sort of not necessarily always distinguish to you whether there's only a causal relationship, an ancestral relationship, or both an ancestral relationship and a common cause between two variables. They sort of hide information in a sense. So let me say what I mean by that. So the interpretation of a MAG is that if you have a directed edge from xi to xj in a MAG, then xi is an ancestor of xj in the underlying DAG that was used to construct it. So ancestor meaning that there's a directed causal path in the underlying DAG, regardless of what I marginalized out. And so if I think that's what it means for it to be a cause or have a causal influence on xj, then that sort of property is being preserved here. The bidirected edge means that xi is not an ancestor of xj, and xj is not an ancestor of xi. So which implies in this space of latent variable DAGs that there's a latent common cause of them both, since those are the only ways in which you could have that non-ancestrality relationship and still have a dependence. So the kind of idea is that arrowheads in a MAG tell you about ancestrality and non-ancestrality. And that's a less intuitive concept than like direct causation in a DAG. There's no notion of direct causation that quite fits with a MAG because you've marginalized out a bunch of stuff. So it might be that the path was very indirect, but it ended up with an ancestral relationship between xi and xj. And the key is that an ancestral relationship and latent confounding can coexist. So just because all I said was that xi is an ancestor of xj, but I didn't say there's also no common cause between xi and xj. So in particular, a directed edge like this in a MAG is sort of ambiguous between the underlying model has no confounding versus the underlying model does have some confounding. right? There is such an L and an ancestral relationship coexisting. And we'll get a little bit later, we'll get to a criterion where you can sometimes distinguish between these two possibilities from a mag, but it's not as direct as just reading the graph. Yes.
Maybe this is something very simple. So there's a true model X union L. So obviously you can always model with an ADMG, but can I always model it with one of these? I haven't understood if this is like fully expressive or what.
Yeah, good question. So for any starting DAG over X and L, I can construct a mag that satisfies these properties from that underlying DAG. And what that thing will represent is the ancestrality relationships in that underlying DAG, and it'll preserve conditional independence relationships using M separation among the marginals. It will not tell you everything that you might want to know about that underlying DAG. As a quick example, it won't tell you how many latent variables there are, right? Like it's not fully informative about all aspects of the underlying structure.
Well, that's something we couldn't even ask for because but it won't tell you the minimum or it won't, or.
No, it won't tell you, it will tell you basically only what I just said, ancestrality relationships and M separations. Yeah, I think here, well, I was gonna say, this is the construction, so, but I can answer this question.
Also a clarification question from Zoom. Is a mag a special case of an ADMG that rules out the counterexamples with extra assumptions on the structure of the graph?
Counterexamples.
So we need counterexamples that you have missing edge. I take it counterexample is that you didn't have an adjacency. So you had deconnection.
Yes, yeah. So I'll get to that on this next slide with an example of how that works. So let me. So go ahead.
So just to clarify, can we represent this graph max?
No, so a mag will never have this substructure. So if you have, if this is supposed to represent a situation in which there really was an L that was like a common cause of these two things, the mag will sort of hide this by adding extra edges. So it's not like you can't represent this thing, but it won't look like this. Yeah.
Well, I was thinking, there was the yesterday's tar example is a very small example that would be disallowed. So what mag would you give for that?
Tar example, that was a front row graph?
The X to Z to Y with a link between X and Y.
Yeah, so in that case, it's going to put a directed edge here instead of a bidirected edge. But that directed edge is sort of hiding this latent variable. So if I start with that graph and I write down the mag projection of it over X, Y, and Z. So this tells me true things about ancestral relationships. It is true that X is an ancestor of Y, and so that's represented in the underlying graphs. That's represented by this edge here. And Z is an ancestor. That's an ancestor of Z. And Z is an ancestor of Y as well. And all the M separations over the X, Y, Z are also preserved. Namely, there's none of them. And that's it. So this edge is sort of like hiding the unmeasured confounder there. But there's a criterion that we'll get to a little bit, which you can learn sometimes whether it's hiding a measured confounder or not.
And we would have the same graph, even though we didn't have that latent phase.
You mean if this was the truth, if there was no L at all?
And the corresponding maximal ancestral graph would be the same.
Yeah. Okay, so then the definition was, there's a lot of words on this slide.
Hold on, could I just make a quick comment there? If the DAG was X to Z to Y, then the mag would not have an edge from X to Y. Right? Just
DAG is X to Z to Y.
What else can you put in?
if there was no confounding between X and Y.
Oh, sorry, you're right. Yeah, you're right. So there's no direct edge, right? So if this was true, then the mag is actually just this. And that's because of this part of the definition. So adjacencies in the mag come from these things called inducing paths in the underlying DAG. So an inducing path is like a somewhat, thank you, Thomas, for the correction. some inducing path is like a somewhat confusing definition to look at, but the intuition is that these paths, inducing path through L induces a conditional dependence between the endpoints of that path after I've marginalized out L. So like the simplest inducing path is just like the direct common cause thing. So if I have Xi and Xj, so intuitively L induces a dependence between Xi and J. And there's a path, so that definition is kind of vacuously satisfied because there's no colliders on the path. And so it's a path in which every vertex except L is a collider. L is not a collider, and induces dependence between Xi and Xj. But it's a bit confusing to go from this definition exactly to that property. You'll have to trust me on it, I guess, for now. But you can prove that if there's an inducing path relative to L between Xi and Xj, then there'll be a deconnection between them in the underlying graph. So the construction then, the latent projection going from latent variable DAG to a MAG over just the X's is one that decides adjacencies first based on inducing paths, and then orients those adjacencies based on ancestrality. So if Xi is an ancestor of Xj, then orient it as Xi to Xj. If the reverse is true, orient in the reverse direction. And if neither is an ancestor of the other, put a double-headed arrow between them. So it's like a somewhat more confusing version of the latent projection operation for ADMGs that requires this auxiliary concept of inducing paths. And how does that play out in terms of the example, the counterexample for maximality we saw earlier? So earlier, the ADMG we saw was like a latent projection of this graph, right? So it had a bidirected edge between X2 and X3. And if you carry out the MAG latent projection for that graph, you end up sort of filling in that non-adjacency that we saw earlier that didn't have any corresponding conditional independence with an edge. So they're adjacent. So namely, because there's an inducing path between X1 and X4 relative to L. So it's a path in which, going back to the definition, on which every vertex not in L is a collider. So there's a path in which this is a collider and this is a collider, and induces the dependence between X1 and X4. So this graph on the bottom, this latent projection, MAG latent projection of the original DAG, again, is kind of informative for in the sense that it's not lying to you about ancestral relationships, but it's less informative than the general ADMG because it's sort of ambiguous about what this edge between X1 to X4 means. Is it hiding unmeasured confounding or not, and so forth. Make sense? So, given all this, we can represent an equivalence class of maximal ancestral graphs with a single graphical object. So this is like the equivalent or the analogy to a CP DAG in the case of DAGs. In the case of MAGs, we have PAGs. And if you spend enough time in causality research, acronyms just become like they flow over you and they don't matter anymore. So CP DAGs is to DAGs as PAGs are to MAGs. And you didn't get that? And PAGs are special in that they have multiple edge types to represent ambiguity about Markov equivalence. In particular, they have these additional circle marks where the circles hide or underdetermine whether there's in fact a tail there or an arrowhead. So ultimately, you can have, 6 kinds of edges in a PAG. You can have a directed edge, a bidirected edge, a circle arrow edge, a circle edge. Actually, that's it for without selection bias. But if you allow undirected edges, you can have those as well as too. So this representation of an equivalence class tells me that there's some MAG in the equivalence class in which this is a bidirected arrow, for example, and some mag in the equivalence class where it's a directed aerial from 5 to 4 and from 4 to 5 and so forth. But also a tricky thing about reading tags is that not necessarily all combinations of filling in the circles can exist at once in the Markov equivalence class, right? So if I filled both of these circles in with an arrowhead, that would form an unshielded collider at x4. And so that's not really part of the equivalence class, because otherwise I would have oriented it as such. And so it's really just saying that there's some graph in the equivalence class in which that's an arrowhead, and some graph in the equivalence class in which that's a tail, and same for that circle as well, but not necessarily that they're all, every combination is equally possible. Okay. So as a kind of example, this is a really nice paper by Jiji Zhang in JMLR from 2008 that goes through a lot of properties of mags and pags. Oh yeah.
Hey, I just have a question about the circle edge actually. So is it true that, so as far as I understand, if you have a circle, that means essentially that in the equivalence class, there is at least one graph mag where there is a arrowhead and at least one where there is a tail. But if you have a circle edge, does that imply there will be a bidirected one in the equivalence class? Or
No.
yeah, it's just about circles, right?
Yeah, good point. So it's just about filling in circles, not necessarily entire edges. Thank you. So as an example, this is from this paper as like a small graph. So there's a small latent variable model. You have a bunch of observed things, and you have an unmeasured latent so-called profession here, which influences income and smoking behavior. And so you can ask, like, what are the different mags that are latent projections of this latent variable DAG? And here are two Markov equivalent mags, which differ in their arrowheads, right? So in this case, I have an arrowhead at I. In this case, I have an arrowhead at I. In this case, I don't. And an arrowhead at parent smoking habits versus not. And I can represent that whole thing with a tag that places circles at those key locations. Okay. Okay. So given all that background machinery, we can now define a PC-style constraint-based model selection procedure that searches in the space of tags. And it can operate in PC like PC in the sense that it just needs to look at every pair of variables and test conditional independence constraints given possible separating sets. And when it finds them, it can remove an edge. And then it has to do some logic similar to PC to orient edges with arrowheads when it finds unshielded colliders, and then propagate some additional rules that basically follow from the abstract properties of the class of mags or pags. Kind of key difference is, so if you look at this and you kind of compare to PC, not that I think you've memorized PC, but it should sort of look familiar to you that you're looking at like subsets of adjacencies, testing some conditional independence thing, and if you find it, you remove an edge, except here now you're starting off with a complete graph where you have circle edges everywhere. You remove circle edges whenever you find a conditional independence. And then you orient things using the collider rule again. So basically I put arrowheads to replace the circles when I find that they're pairwise, I and K are adjacent and K and J are adjacent, but I and J are not adjacent. And that K is not in a separating set. So that's all. So like this whole first stage is exactly the same as PC, except with circle edges everywhere. And I'm using, by the way, this asterisk here to denote like it could be any symbol. It could be a circle or a tail or a arrowhead. And then there's an additional step where now you kind of have to do the whole thing again, but looking only at subsets. When you're searching for separating sets, you have to look at subsets of this specially constructed set called PDS, possible DSEP. So the definition of which is down here at the bottom. Sorry, it's a bit small. But possible DCEP is a set constructed based on the location of adjacencies and colliders in the graph, which has this property that if there exists a separating set between xi and xj that's a subset of x, it must be a subset of possible DCEP. So you can show that for mags and pags that these separating sets are all contained in this like relatively large set called possible DCEP, which is like you can construct from partial orientation information about the graph. It's sort of the analog to, in PC, we said that if there's a separating set, it must be a subset of one of the parent sets of the two endpoints, right? So this is the like more complicated version of that. If there's a separating set, it must be a subset of this possible DCEP set. And so that means that effectively, like this whole first stage of the algorithm is really just instrumentally useful to determine what possible DCEP is for every set of variables. And then you sort of do it again using possible DCEP as your set of potential separating sets. So I'll go through and I'll look at every pair of variable, and I'll look at subsets of possible DCEP of increasing cardinality, and I'll remove an edge if I find a separating set, and I'll save which one did it. And then I'll repeat step 9, which means basically orient all the colliders as we did previously. And then at the end, I'll apply a set of orientation rules. The orientation rules, I didn't reproduce on these slides. They're in this paper. They are, the first few orientation rules are just the same as the PC ones. They basically prevent cycles and new unshielded colliders. And then there's some additional orientation rules that follow from the basically the ancestrality property of mags and preserving the Markov equivalence of mags. So I won't go into that here. But that's FCI. So let's see. Let me end, before going on to the next bit, let me end with like a kind of quick demonstration to maybe prove to you this isn't magic, I guess. Because oftentimes when you present the FCI algorithm, it seems kind of crazy that you could learn anything about a latent variable model. So really quick, just using a popular R package for causal discovery called PCAlg, I'm going to simulate a little bit of data on 5 variables with 1 latent variable. So the true graph that I'm simulating from in this first little bit is one that we saw on our slides earlier. So it's the one where x1, x2, right? So where L is latent. And so if you simulate, I'm going to do a sample size of 10,000 so that I can be relatively confident it won't make statistical mistakes. I'm simulating from a linear Gaussian model here with just coefficients that I made up. So I'm going to use the independence test for Gaussian data, the Fisher-Z partial correlation test. And then I'm going to run FCI. Sufficient statistic is just the data. It's the covariance matrix. And the sample size independence test is the test that I choose to plug in. I'm setting the alpha to 0.05 because it doesn't matter for 10,000 variables at this point. The number of variables is 4. So the data only consists of x1, x2, x3, x4, not L, because L is latent. And I'm printing out verbose output just for fun. And then the graph that I get out at the end, the default visualization for graphs in R is pretty ugly, but there's better ones out there. But the graph you get out at the end is what you expect from the PAG representation of this thing, right? Namely, it puts, if you can see, it puts a bidirected edge between 2 and 3. It puts arrows into 3 from 4 and into 2 from 1. And then it leaves circles here to represent the Markov equivalence. So it's going to estimate this PAG. And so here it did exactly the right thing. because I gave it enough sample size and it's only 4 variables and it's not a very hard problem. But it gives you exactly the PAG representation of this underlying DAG. Okay? And as another example related to what we saw, and actually, just for the sake of comparison, what if I ran PC on this data, you might ask. So if I run PC on the same data, I get something that orients an edge in one direction or the other incorrectly, as we saw before, right? It finds the right set of dependencies in a sense, but it messes up the orientation because it has to decide at some stage whether x2 goes to x3 or vice versa, or leave an undirected edge between them. And in this case, based on the order of the tests, it'll just orient it this direction. And so it'll be sort of correct about some stuff. It's correct about 4 to 3 and 1 to 2, for example, but it's incorrect about the relationship between 2 and 3. And you could do exactly the same thing with GES, although it's a little harder to predict what it'll do. So for GES, I can define a score. And so this is the Gaussian BIC score. I can run GES and I can plot the result. And I similarly get a DAG that's like kind of wrong, right? So it'll, in the case of GES, it gets so confused about the relationship between x2 and x3 that it just decides to cover it so that there's no independence at all. Okay? And as another example, was there a question? Yes.
So is there tests that are for non-parametrical tests?
Yeah, so I mentioned this in the morning presentation that there's a large literature on non-parametric independence tests. The 2 ones that I discussed really briefly were this kernel-based conditional independence test, which uses basically kernel regression to define a test statistic. And then this generalized covariance measure test, which uses the expected conditional covariance as the parameter of interest and does some sort of non-parametric or semi-parametric estimate of that thing and tests whether it's 0.
I was trying to use it, but I looked at the documentation.
It's in separate packages typically. So if you look at the slides from this morning, there's a package called cond-int tests, conditional independence tests, and that includes KCI and a few others. And then other packages are kind of available from the authors or on CRAN or whatever. But once you load in that package and you define the test as I did above, you can just plug it into PC. Okay, so let me do another example with that kind of Y-structure graph, which is kind of key to orienting things in FCI. So in the Y-structure graph, I'm assuming here that the true DAG is Z1 and Z2 affecting X, which affects Y, with possibly this unmeasured confounder L between X and Y. Okay? And so I'll generate again 10,000 data points from a model that satisfies this. So you can see that here I have like that Z1 and Z2 affect X, and L affects X, X affects Y, and L affects Y. And I generate data from that model. I just keep the measured stuff. So this is just 4 variables again, Z1, Z2, X and Y. I define the same conditional independence test and so forth. And I find that if that was the truth, this is the graph that I learned. Namely, it puts an edge between Z and Y for both Z1 and Z2 because they're not deseparated given X. Right? In the original example, we saw that if this L is really here, then Z2 and Z1 are both not independent of Y given X because of this deconnecting path. Whereas if instead I do this again, making L no longer a confounder. So I just set the effect of L on X to 0 and generate the data again and run FCI again. Then it returns that there's actually no confounder between X and Y, right? It gives me a directed edge between X and Y, and Z1 and Z2 are not ancestors or are not directly connected to Y in this PAG. And there's some circle marks to represent ambiguity related to Markov equivalence. And this is an example of, I'll get to this after the break, but the directed edge here, actually I can read off from this graph that it doesn't hide a confounder. In general, I wouldn't know, right? Remember we said that the directed edge could kind of hide, it could mean that ancestrality coexists with unmeasured confounding, but there's a criterion I can use, which is satisfied by this graph, that tells me that there's no confounding between X and Y. And so I'm learning things are really, that there's an ancestral causal relationship between them, but no confounding relationship between them. And so like these kind of Y structures end up being very useful in FCI or related algorithms for distinguishing between unmeasured confounding and ancestrality versus just ancestrality. Okay? Yeah.
The circles by Z1 and Z2. So those represent that there could have been it needn't have been a directed edge there. It could have been a latent between.
Yeah, there could be a latent between X and Z2 or X and Z1. Yes. So that could be oriented as a double-headed arrow. Yeah. Okay, so I think it's break and we can pick up after the coffee.
Great. 30-minute break. We'll be back here at 3:30 for the last round. Thanks.
Yeah.